detailed for you. And if you're very familiar with machine learning, then I think you may already know all of this stuff. I'm sorry to disappoint you. It's not going to be super detailed. Yeah, so beginning with the whole hype around machine learning and AI. So this is a quote from Jeff Hinton, who is one of the pioneers of deep learning. Uh, he says we should stop training radiologists now. It's just completely obvious that within 5 years, deep learning is going to do better than radiologists. Despite this, it's 2021 and the number of radiologists in the US have grown by 7% since this date, and we are still in a shortage for radiologists. So clearly, like something has not worked out according to Mr. Hinton's projections. Yeah, this is also a great sort of quote to start off this talk, given that the whole reason why we are doing this talk is because this is a super interesting area and a lot of people are interested in this these days. So it's very important to not get carried away with the hype and kind of understand the nuance and why this works, where this works, and where it does not work. Um, so this is one of the most interesting uh, observations in machine learning over the last few years, in my opinion. So this is an adversarial example, and this kind of relates with the hype and why we need to sort of understand how these systems work and where they don't work. So for the people who are not familiar with this, on the left, so this is a image classification task where we kind of need to identify what the image topic or what the image is. So on the left, you can see the image of a panda, and below you can see the output of a model that guesses that it's a panda. And this it's like 57.7% confident about this. Uh, but then you can find a certain vector, which is this, like it's a very tiny vector, which looks like a random noise. And when you add this vector to this image, uh, the image visually stays the same. It still looks like a panda, but the same model that produced panda in the first image now produces output gibbon, which is a kind of a monkey, and which is wrong. And it produces this output with 99.3% confidence. So it's absolutely confident that this is a gibbon. And this is super interesting. Like if you've heard of how convolutional neural networks work, um, they sort of tend to identify edges and lines and colors, and then in the deeper layers, they try and identify more complex characteristics like kind of shapes and objects and certain features. And this is very similar to how the human optical system works, and how CNN started were actually inspired from the human optical system. Um, but this is something that the human optical system can never fail in, but you have the machine learning model actually failing. So this is a real thing. So there are adversarial attacks. So in this case, this is an example of like on the left, you have the MNIST data set with the digit recognition task, where where you can see on the bottom row that this is a 0 and the model guesses that to be a 5, and this is a 3 and the model guesses that to be an 8. And you can sort of create this random noise given any model and any input, like including the most advanced models and advanced inputs for this. And this can be potentially sort of destructive. So on the right side, you have a self-driving car dataset in which you have sort of images on the top with the correct signs, and on the bottom you have images of like traffic signs with an adversarial attack, which changes the output of the model on these kind of inputs. Yeah, so basically, why do adversarial examples exist? This is like a question I'm not trying to answer in this talk. Like there are a lot of articles that you can go back and look up yourself. But what I'm trying to motivate here is we need to sort of think of machine learning models uh, as pattern matchers, like and mostly doing pattern recognition, and they have like clear failure cases that we sort of also need to be aware of. So sort of ML is suited to certain types of tasks is what I'm trying to say. So on the left side, you have digit classification, where like given a handwritten digit, you want to identify what the written digit is. And this is pretty much a solved problem for us. Um, we we have achieved really high accuracy even on really messy handwritings in this problem. On the right side, I'm creating a hypothetical problem in which you, given a joke, you want to classify if the joke is funny or not. Um, and I don't think like our current state of machine learning is suitable for such kind of problems. To think of it, this is a hard problem for humans as well. It's not easy to come up with funny jokes or even tell if a joke is, you, or kind of explain why a certain joke is funny. Um, It involves several elements such as having real world knowledge. Like you could make a political joke or like a joke on, I don't know, something else which requires you to know about the political scenario or something like that, which it's not very easy for like we don't have techniques developed to model these kind of things. We kind of getting close to them where there are efforts that trying to develop these kind of things as well. Um, but yeah, so this is like a contrast between problems that we can solve right now and which we are certainly not there. Okay, with that brief intro about hype and about just thinking about how to apply machine learning and where to not apply it, I want to go into one of the areas I'm really interested in called self-supervised learning. And this is sort of the build up to that where I explain why we need self-supervised learning. Um, so machine learning and like image classification really took off with ImageNet, where we had this first large scale data set. So I think ImageNet contains around 1 million images. And the task is to classify the images into 1 out of 1,000 categories. So this graph sort of shows the error rates on ImageNet over the years. And as you can see in 2010 and 2011, we did not really have like this is sort of pre-deep learning. So the models were shallow. There were handcrafted features being developed. 2012 is where you can see like the error rate drops from 26% to around like 16.5%, which in like ImageNet land is like a landslide drop in error rate. And this in 2012, this is because of the model called AlexNet, which was the first working implementation of a CNN that kind of drove this change. And since then, there has been an explosion in deep learning. It has uh, been extremely popular in academia and in industry as well. And there's been like a lot of researchers working on it. And as you can see, like the error rate has been dropping ever since until 2015, where the error rate falls below 5%, which is a very interesting baseline, very interesting benchmark to beat, because that is also the human error rate on ImageNet, which means we're actually doing better than humans on identifying images in this data set. Um, uh, this particular breakthrough was because of the model called ResNet, which introduced this concept of residual connections. And what these residual connections did was they allowed you to bypass certain layers in the model. So you could be a little less careful about how many layers you're including in your model. And the model sort of learns the which layer to bypass and which layer to not bypass. And as a consequence of that, you could make your models really big, and really deep. For example, the biggest ResNet model was 152 layers in this case, compared to the VGG in like 2013 or 14, which was maybe 16 layers as the biggest model. Yeah. So what are sort of the driving factors that have led to the advances in machine learning? So talking about one uh, looking at the last graph, as I mentioned, the models have gotten deeper. So uh, one of the biggest uh, things has been to make the models larger, to have more number of parameters, which gives the model a much higher capability to model things. Um, in vision, we have CNNs, residual connections, and this has made it possible to train models up to 152 layers deep. Now, NLP also had its ImageNet moment in which we sort of were able to use transformers with really large pre-training to have really large models. So for example, the T5 has 11 billion parameters in the model, which is really, really large. Um, the other thing that's driving a lot of advances is data set size. With larger models, you also need more data to make the best use of sort of the modeling power that you have. For example, in NLP, the Common Crawl dataset contains 2.8 billion web pages, and that's like a huge dataset for pre-training models in NLP. Um, However, if you think of vision, it's not, uh, there is no famous large-scale computer vision dataset either on images or on videos that easily comes to mind or that has gained popularity. Um, and why is that sort of? So this is because we actually need human annotations to annotate the labels onto images or videos. And in case of vision, that's just not possible to scale up. It's a lot of manual work. In case of NLP, the task is less supervised, so you don't need annotations. Like you can just extract text from the internet or text from books, for example, and just train language models on that. But that is not the case with vision. With vision, you need supervision, and you need like someone to annotate your data with labels. Um, so this is sort of where self-supervised learning comes in. In this, we sort of don't need label data, and we obtain the supervision that the label would have provided from the data itself. And this is done by using a contrastive loss. And I'll sort of explain what a contrastive loss is after this as well. Um, so the goal here is to pre-train the model on a really large data set, which does not have labels. So think of like just in case of like video classification, think of just downloading or scraping all of the videos on YouTube and creating a very large data set to pre-train your model on, and then fine-tuning the model on a smaller target data set, which may have only a small fraction of the data as the original data set. So such data sets actually exist now. So there's a data set called How to 100 Million, which contains 100 million YouTube videos. And you can compare this to um, supervised video datasets, where the largest one is a dataset called Cynaptics, which contains around just 700,000 examples. So we have around 100x more data if you kind of don't need to use the labels. Okay. So how does self-supervised learning work? So this is an example of a typical architecture in which we're trying to learn the embedding of, we're trying to learn like just the embedding of this image of chess pieces. You have two, and so what we actually do here is we do some data augmentation and create an alternate image from the original image that is either a rotation or a crop of the original image. So because we have created the image in this fashion, we know that this image is same as the original image in its semantic meaning, or in the topic that we have to assign to this image. We then have an encoder. An encoder could be any model of your choice. It could be a CNN, a transformer. And we encode both the images, X and Y, to obtain embeddings H and H dash. I'll use the word embedding very often. And what I mean by embedding is just a vector, like say a small dimension like 64 or 100 dimension vector. So you take both of the images, you sort of have your deep neural network, and you encode these images into vectors H and H dash. And then you apply a contrastive loss on these two vectors. So what the contrastive loss does is if H and H dash come from semantically similar images, then you need to bring their representations closer. Or like, for example, if you're using cosine distance, they should have smaller cosine distance, or L2 distance should be smaller between H and H dash. And the reason why this is called a contrastive loss is in case of negative samples, you need to push H and H dash as far away as each other from possible. So sort of increase the cosine distance or increase the L2 distance between H and H dash. So in this case, we have the original image of the chessboard, and then we have another randomly sampled image. In this case, it happens to be a cat following COVID norms. And you sort of encode both these images to get your H and H dash, and you do your loss between them such that you push them far away. So as you can see, like all you needed was to create positive examples, you just needed to do some data augmentation and crop the image or rotate the image to get your semantically similar image. And in case of the negative sample, you just needed to draw a random image from your data set to create a negative sample. And you don't need like supervision, like you don't need images to be annotated here, and you can still learn these kind of encoder models using this loss. How do you end up using these models? So then you can, after you train in this kind of a setup, you go back and just use the encoder part of the model to produce an embedding, or you can add a head, like which is a simple linear layer on top of the encoder to sort of train on a downstream task, or like fine tune on a downstream task, which has supervised labels. So this is an, okay, I'm not sure how we are doing questions, but I think I'm kind of, yeah, maybe I can try and take questions. I see someone has raised their hand. Can you all speak up on the mic? Or? Okay, maybe I'll try and get through this section and then we can open it up for questions later. So this is one of the self-supervised approaches called SimClear that uses the contrastive loss. And you can see like, so this is a plot of the model size versus its accuracy on ImageNet. That's the task we saw in one of the earlier graphs. And you can see like, this is the point where we have a supervised ImageNet task getting around like 80% accuracy. And like just using this contrastive loss on ImageNet, we're actually able to beat the supervised accuracy, or at least match the supervised accuracy, which is pretty cool. It means that you can perform as good on a data set even without the labels as you would do with the labels. Okay, so this is another approach called generalized data transforms. And this one is a contrastive loss applied to videos instead of images. So remember, as I said, the self-supervised learning is actually like just a framework to train models, and you can apply it to images, videos. You can apply it to speech, like for speech recognition, or basically any other kind of data which in which you can create these kind of positive and negative pairs without needing human labels. So the way they adapt this technique for videos is in videos you have speech signal. So you can see over here you have an image, like that's the visual part of the video, like a frame of the video, and then below it you have the audio spectrogram for the video. So you take multiple videos, and what you do is you do a contrastive loss between the frame, like the visual part, and the audio part, and you try to bring these two together in like your embedding space. And again, when I say try to bring them together, what I mean is you want to minimize the distance between their vectors. Um, yeah, and similarly, like if you take this image, you want to bring the visual part and the audio part closer together in the embedding space. However, between two different videos, you want to have repulsion in the embedding space, and you want to increase the L2 distance between their embedding vectors. Um, so we're sort of building up on the idea we saw in the first the image task, where we just use image and image crops. When applying them to videos, we actually use videos and like the visual part of the video contrasting with the audio part of the video. And this is super cool. Like in this case, like you can sort of, you can see that the model ends up learning correspondence between what's happening in the video, like the person playing the guitar, like in this last video, and the kind of sound that the guitar makes. So these are some more results on how the GDT model performs. Um, so there are kind of two tasks. Like on the left side, we pre-train the model on the Cynaptics dataset. And as you can see, like on the UCF dataset, the first row is the supervised benchmark, and the ones in the middle are all self-supervised techniques, and the last row is the GDT. So the GDT beats all of the other self-supervised techniques, but we don't really beat the supervised technique in this case. However, if we use other data sets for pre-training, so this goes back to how I said you can use a much larger data set for pre-training and then fine-tune to a smaller data set, then that's where we actually end up beating the supervised technique as well. So both on Kinetics and both on HMDB and UCF, the supervised accuracies are 70.4 and 95.0, and the GDT can score accuracies of 72.8 and 95.2. And you can see the data set that you're pre-training on. So this is the how to 100 million data set that I mentioned, which is scraped from YouTube. And this one is the IG65 million data set, which is a similar one, but scraped from Instagram instead of YouTube. So these kind of self-supervised techniques allow us to leverage like really large image or video data sets of like sort of our crowdsourced platforms like YouTube or Instagram, and this is sort of the current frontier in image and video understanding. Uh, Another fun fact is that this is actually a work done by some of my colleagues. So you can check out the paper here linked on the bottom of the slide. It's a pretty cool paper to read as well. I can probably share the slides after the presentation is over. Okay, so this sort of ends the first part of the talk on sort of self-supervised learning and where we are at in terms of video classification and image classification. I'm going to switch to ML in the industry. And maybe we can do questions all at the end since I'm kind of like just barely at time. All right, so I have not worked in academia, but I've done a bit of research in the industry. So I'm just going to try and compare industry and research just a bit. Um, I think the main difference is that in research, we're kind of trying to push the state of the art and trying to advance our capabilities, while in industry, the main focus is to improve certain business metrics. Uh, so there is more focus on kind of taking an existing uh, technique from academia and kind of adapting it to the industry in a way that it kind of handles industry challenges. And the biggest challenges here are handling scale. Like academic data sets are kind of small, like 10,000 to 1 million rows, 1 million like samples typically. In industry, you kind of encounter user engagement data, which can be like a million to sometimes even a billion samples in your train set. Um, uh, in academia, your data sets are often clean, like someone else has spent effort to clean the data set such that others can just focus on training models and developing techniques. That is not the case in industry. You have to sort of prepare your own data sets, and a lot of time is actually spent in preparing the data set, cleaning it, figuring out things like how to normalize it, things like those. Um, yeah. Okay. So with that intro, I'm gonna so the other biggest difference is the kind of tasks that are useful in industry versus in research. Um, so one of the most common tasks in industry is the task for retrieval systems. And this task does not get too much attention in research or in academia because it's mostly an industry-oriented task. So I'm going to talk a bit about retrieval systems as it also relates to my work on video recommendations. Um, so what are retrieval systems? So I think you are familiar with these already, but it's just in a different form. Um, the problem here is to retrieve relevant content for a given query. And so to frame it mathematically, sort of you have like different queries and items, and you want to retrieve the item with the highest score for a particular query. And like this is a very popular task. So you can think of Google search, right? You have a query and your items are sort of the web page results that match the query. In case of Instagram, you're like think of Instagram feed in which the query is the user that needs the feed. And the items are sort of all the posts in the feed that are relevant to the user. Amazon, like you type a search query for products and the sort of items are all the products themselves. This is also occurs in like Spotify for music recommendation, where the query can be either like you searching something or just on your home screen. We need to sort of recommend music for a particular user. And similarly with YouTube, like you could search for videos, or you could on your home screen, like you could sort of have videos recommended to you without you actually searching for them. Um, yeah, so I'm going to sort of take the example of YouTube homepage recommendations, and I'm going to sort of discuss how like a very, very basic system for recommending YouTube videos to a user would work. So basically, we sort of need to model a score between users and videos. So we kind of go back and do like we find the score between a user and like multiple different videos and show the user videos that get a high score for that user. So this is sort of like the task to model this the score function. So the score function is any deep neural network that takes user and video features, and it makes a prediction about how interested is the user in that video. And then you have to train this kind of a model, you have uh, a loss which consumes a label. And in this case, the label could simply be like, did the user watch the video or not? And you can sort of train the model to uh, increase the score for videos that the user has watched and decrease the score if the user has skipped the video or not clicked on the video. Um, so how do you use the score function and what are the problems with it? Like, so if you need to recommend videos for end users, and you have a pool of videos that you need to recommend from. So in this case, think of like YouTube, right? So YouTube maybe has say 500 million users and also contains maybe like 100 million videos. So you actually need to run the model n times v, like nv times, uh, so that you can score all the videos and then pick like the top k videos. And this is really expensive. Like you don't want to run the model uh, for each user for every video. So like I guess this is sort of the challenges in the industry. Like a lot of the work is focused not only on developing the best model, but also developing a good model that you can actually use in a production setting to like serve millions of users. So this is like a very simple way to scale up this kind of a model. Um, what we do is instead of having this one single model to encode both users and videos, we kind of split the model up into a user encoder and a video encoder. Each encoder will produce the corresponding embedding. So we have a user embedding and a video embedding, and we will then do a cosine loss between um, these two embeddings. And once again, like the cosine loss is a loss that brings the user and video embeddings closer distance-wise if it's a positive sample. And if it is a negative pair, then uh, you will increase the distance between the user vector and the video vector. Um, so ultimately, we have this kind of a setting to train the model. And after we have the user and the video models trained, uh, you just extract these embedding vectors for all the users and all the videos. And you run the k nearest neighbors operator on the users and videos to sort of get your top k nearest neighbors to a particular user's embedding. So to do this kind of a setup, you just need to run the model like n times for all the users and v times for all the videos compared to n cross v in the previous kind of approach. So this is one sort of basic technique that's also used in the industry. It's called the two-tower model, where the user tower and video tower are sort of separate model towers. Yeah, and then there are several more optimizations here. Like there are multi-stage models. Um, in multi-stage models, we sort of have a very simple model in the beginning, which takes in like which is run on all of the users and all of the videos to create sort of a short list of some users and videos. And then you have a much bigger model that's more accurate to refine the short list into the top N videos that we actually want to show to the user. Yeah, so that was sort of on the scaling up part. I'll quickly transition to sort of what my industry experience has been and also give a bit of it's sort of a bit of an idea on like what is it like to work as an engineer in the industry. So I joined Facebook as an intern in 2017, and I worked on speech recognition. When I mostly worked on developing infrastructure to deploy our speech models into like services. Um, then when I joined full time, I worked on natural language generation for Facebook Assistant for around 2 years. So Facebook Assistant is similar to um, like Google's Assistant or Siri, and we have it running on our hardware devices called Portal. In this case, the task was to um, kind of run the assistant query and get the structured output of what we want to tell to the user and express it in natural language text so that we can use TTS to like say out the response of the assistant. And since 2020, I switched teams and I'm working on video recommendation for Instagram Reels. So the the few slides before that I spoke for the architecture stack for YouTube recommendations, I think a lot of recommendation systems, including Reels, use like some sort of setup similar to it, which is sort of most relevant to the work I'm doing right now. Okay, we are almost towards the end of the presentation. So um, this is one of the last slides, and this is what a typical machine learning stack in the industry looks like. Um, we start off with data pipelining. And what this means is you want to process, uh, say, like your user and video interactions. Like you want to kind of, in case of YouTube, like you want to process which user watched which video or skipped which video, or like YouTube also gives you an option for not interested. So you want to kind of track which user clicked not interested. And there are like millions and hundreds of, like tens of millions of these kind of data points coming in every day. So in the data pipelining step, you want to process like these large number of data points into something that you can pass into your model for training. Um, so to process these kind of like this scale of data, there are like specialized techniques that in the industry. So Spark is mm, one of the most famous ways to sort of do distributed data processing. And the main paradigm behind Spark is like you just if you have a lot of data, you throw a lot of machines at it. Like it's kind of splits up the job into and runs it on maybe 100 or even 1,000 machines at times. It's the same with the remaining like Scala, Presto, which also help you kind of do distributed data processing. Lastly, Airflow is a service that orchestrates your different processing tasks. So you can sort of do multi-step processing using one of the previous technologies like Spark or Scala. The next step is to specify the model. It's like what is the architecture, what is the loss function. So I did, Facebook typically uses PyTorch for this. TensorFlow is the obvious other candidate here. You would typically also use a modeling framework. For example, Classy Vision in case of image recognition. Keras is a very popular one. Um, FairSeq is another one for NLP, for sequence-to-sequence modeling. These frameworks typically contain common models or common model layers like CNNs or transformers or LSTMs. So you don't need to code up these model layers each time. Yeah, so the next step is to train the model. And of course, like since we have like super large model as well as a large data set for training, like maybe like hundreds of millions of samples and like model size in like several GBs in this case. So the model is kind of the training happens on a GPU cluster with like multiple GPUs. So there is also software to manage distributed training on these kind of clusters. Um, there are also distributed training algorithms, which figure out ways to average gradients in efficient ways so that you can backpropagate um, sort of your uh, in this kind of a distributed setting. The main challenge here is that you split your data among, say, you're training on 4 GPUs. Your data and model is split on 4 GPUs, where the model is actually copied. And you need to find a way to aggregate gradients from each GPU such that you can update all of the models. Lastly, we also use a tool to monitor metrics such as TensorBoard. Like it's very important to be very organized about tracking like metrics when you train your model. And TensorBoard is a really amazing tool for that. Okay, so then on over to the right side. So once you have your model, you want to optimize it so that you can run it at scale. And one of the most common optimizations is to use quantization, in which you change your weights from like using double or 64 or 32-bit floating point values to using 16-bit or 8-bit floating point values. So that reduces the computation time by a lot. The other optimization is, or rather something you need to do to deploy your model, is that your model is mostly trained in Python because like it's easier to write Python, whereas the service in which you will deploy your model is probably written in C++, so that it's like highly optimized for speed. So there's something called TorchScript that helps you convert a Python model into C++ and like also run it in a C++ service. We also deploy the model in one of our services. And in this case, the model, like in big companies like YouTube or Facebook, you would have the model getting maybe hundreds or even thousands or 10,000 requests per second. And you need like sharding, which means splitting up, like replicating the model on a lot of servers, so such as that you can handle like this high number of requests per second. And finally, like most companies will do some sort of analytics after you deploy a model, in which you kind of split your users into 2 groups. One group sees the changed model or the updated model, while the another group is the control group, which still has the old model. And then you sort of measure the difference in performance for your group A and group B to see if the new model that you deployed actually is making things better. Yeah. So the last thing is something that's really important and coming up, and it's called fairness in AI. It's super important to think of fairness because a lot of these models go on to make you apply them in like in detecting people, like people's faces. For example, the face unlock on smartphones. Sometimes it works differently for different ethnicities or different races. AI or ML is used in software that sanctions loans and provides insurance rates. In this case, we have seen like the software is to be biased towards certain like communities because of certain biases in the training process and in the data. So it's super important to sort of measure how fair your model is before actually going ahead and using your model. Um, so I think the goal of fairness is to measure the distribution of your model outputs against characteristics like gender, color, ethnicity, and income groups. For example, if you're writing a model for unlocking your smartphone using your front camera, like using the face, your model should not perform differently for different races. For example, like you can measure things like accuracy, or like the time it takes for the model to produce an accurate output, and it should not be high or low for one race such that that race has a better or worse experience than the other race. Bias kind of creeps in through many places. So sometimes the distribution of your data in your training step is biased. Um, this happens a lot in case of like insurance softwares where like certain areas are more prone to crime, and automatically you end up assigning like very high insurance premiums to those areas, even though like the particular house may not be prone to like a high risk for higher insurance rates. Sometimes there is a bias in labels. So the human labeling step, there could be mistakes or noise that leads to like just your labels not being good. Your evaluation step could be problematic, like based on the distribution of your test set. You could use unnecessary input features that could lead to spurious correlations. For example, I don't know, like uh, some models, like some insurance models contain like the age of the person or the race of the person, and these features may not be relevant to sort of what the model is trying to do. Yeah, and this is not an exhaustive list. This is sort of a new area in AI, and there's like work still being done to evaluate why the model is not fair. Yeah, I think with that, I'm pretty much done with my presentation. Yeah, I think I covered a bunch of things, so yeah, feel free to ask questions. I'll be happy to go back and like, redo slides or answer anything that you want to know.
Yes, sir. Thank you so much, sir. We got really good insights into the domains of image processing and NLP. We have a lot of questions for you. Uh, Give me a minute. Let me process those, and we'll start the Q&A.
Oh yeah, sure.
So can we go now for the quick Q&A round?
Oh yeah, I'm ready.
Yeah. So the first question is it's been asked like just a minute. Yeah. How is the training data set with 1 billion samples done? It will take a lot of GPU, right?
Yeah, it does. I think so. If you think of the T5 model that trained on 2.8 billion articles, I think they trained it on like a huge number of, I think like 1,000 GPUs, and they train it for like maybe 1 week or 10 days. So it does. There's no way around it. Like if you have to handle scale, sort of have to scale up your computation. Um, in practice, what happens is you do a lot of your model tuning, like for example, deciding between different architectures and different hyperparameters using a much smaller data set size. So even if you have 1 billion samples, you will just use maybe one like 10 million initially to tune your model. And then when you have a tuned model, you sort of launch just a few runs on the entire dataset.
Yes, sir. Thank you. We have a next a very interesting question. The energy consumed by the GPU for training a model may be huge for an industrial application. Is it similar to the energy consumed in crypto mining? If yes, then there are any steps taken to reduce this energy consumption?
Yeah, that's a good question. I'm not sure how it compares to crypto mining. I think crypto mining is a continuous process, like you need to continuously mine crypto. But model training is probably not continuous. Like you can train a model and then use the model uh, without having to train it again. Um, there is actually a paper comparing the cost of training large models in terms of energy and in terms of the carbon footprint as well. So if you look up like model training GPU cost carbon footprint, you can find a paper on this.
Thank you, sir. The next question was like, it's a general question. At what point during your studies did you decide to pursue ML professionally? What was your knowledge credentials or the level of ML at that point?
I think it was after I decided to do my master's. Um, in my undergrad, I did a project with that involved a little bit of machine learning and sort of like heuristics or like evolutionary algorithms. But that was like very little, and I mostly gained exposure to machine learning during my master's.
Okay, sir. The next
Uh,
question is about like,
I also
hello.
want to add to that. Actually,
Okay.
so that was so my undergrad was more than 4 years ago, right? More than like 6 years ago, actually. So um, things have like AI and ML has become much more popular now, and I think like IITI has like more stuff in their curriculum. So I think like the level of exposure in undergrad to machine learning right now may be different from what I was exposed to.
Surely, because we have a very huge wave of ML nowadays. So like, there is a very big hype about ML. So everyone is like going for it. Yeah, the
Yeah.
next question says like, given the large number of built-in libraries available in Python for AI ML, what does a student or a beginner have to do to stand out? Also, what are the benchmarks or the skill sets do the companies consider while recruiting someone?
Um, yeah, I think libraries are not very important. Um, it's like it's very similar to like learning Python or learning C++. Um, Ultimately, you should be able to solve the problem. I don't think like major companies care about which libraries you know. Um, in terms of skill sets, I think yeah, it's hard to say. A lot of I think Kaggle is a great way to gain skills. Another way is to read papers, uh, like kind of uh, find areas that you're interested in. Like I spoke of self-supervised learning today. You could take like reinforcement learning or like image classification, something in NLP, and like just try and maybe read like stick to one area and read a lot of papers in one area, and that's a good way to develop your skill as well. Um, it's also important to focus on like the math side, like to understand the theory of machine learning. Like you need to know a little bit of linear algebra and statistics. So it also helps if you're strong in those kind of basics.
Okay, sir. Thank you, sir. We have another question. Um, what's your regular working experience like? Is it more of a training and fine-tuning models, or is it working on a theoretical model questions? Like, yeah.
So it depends upon what your role is. Typically, you would have either a role in a product team or in a research team. If you're in a product team, then your role is to develop models and deploy them to product, analyze if things have improved in the product, and then like sort of go back and change things in the model if they have not improved. Um, in that case, you end up spending a little bit of time on the model training and fine tuning, but a lot of time on preparing the data for training the model and on analyzing how your model is performing, and sort of debugging why it's not performing well or what you could do to improve it. In case of if you are in a research role, then your main responsibility is to sort of publish a paper, and in that case, you would sort of spend more time on model training, on like writing model code for different architectures and experiments.
Okay, sir. Thank you. We have a question. What do you see as the most important domains or subdomains coming up in the future in AI ML from a general industry perspective?
Um, so self-driving is one, right? Self-driving is really hyped up. Um, the, Another one is like self-supervised learning that I spoke of today. That helps you sort of leverage a lot of unlabeled data. Reinforcement learning is another one that uh, also sort of helps you uh, leverage unlabeled data. Um, yeah, I guess like you probably want to like the industry will adopt what is the latest in research. So ques- the question you want to ask is like sort of what's the latest in research and what's the research direction, and then sort of stay up to date with that.
Yes, sir. Yes, sir. Hello. Am I audible?
Oh yeah, you are.
Okay. Can you repeat what you said? I had a glitch, I think.
Um, Yeah, so I think like it's very important to stay in touch with what is the latest in research,
Oh, yeah. Yes.
and that's a good way to identify promising areas.
We have a last question. What was the research before SSL?
Sorry, can you repeat the question?
Is it audible now, sir?
Yeah, I can hear you.
Yeah. What was your research before SSL?
What was my research or like the research in the sort of community?
In the sort of community.
Oh, um, well, I think like SSL is fairly new, and before that, you mostly had research on like supervised data sets and improving the architectures. So SSL timeline is probably like 2018 to 2021, and like 2017, 2018 is like when ResNet came out. So you're still trying to like people were still trying to develop like architectures at that point. DenseNet was 2018, I think. So yeah, there was more focus on architectures. Like you could still train models and improve error rates based on like better architectures. But if you look at sort of um, all the way start, if you look at this graph, like as the architectures got better, the error rates started getting lower and lower, and there was a saturation point. Um, so SSL is sort of the next step beyond this saturation point.
Thank you, sir. So I think we're done with the questions. Like I would ask for a suggestion rather than advice. Like we are undergrad students. Like what would you suggest us who are just who are just beginners in ML and AI? What would you suggest us to do? Like what should be the benchmarks that we should follow and all?
Yeah, I don't know what's good advice there. Like I think um I think um try to try to get into research, or maybe try to work on a research problem. It's not easy. Like I think you need to sort of have your prerequisites very strong to take up like research, and if you kind of aim to do that, then you'll also discover that maybe you want to like do research on SSL, but you don't understand some of the basics. So then you'll try to work on your basics first and then get to doing research. Uh,
Thank you, sir.
yeah, that would
I
be my
think
recommendation.
yeah, yeah. I think we have reached the conclusion of the talk. I would now like to give the vote of the thanks. Vote of thanks. Just a minute. Yeah. Thank you, sir. We have now come to the climax. Now I shall present the vote of the thanks. I would like to thank our guest, lecturer of the webinar, Mr. Upasani, for taking out time from his busy schedule and enlightening us with his knowledge and expertise. Today's lecture or webinar was full of knowledge and curiosity. It gave us very deep insights and very new deep insights into the field of ML and AI, more particularly SSL, image processing, NLP, and all. I would also like to thank the Student Affairs at Indore for letting us this opportunity to organize the event. I also want to thank the volunteers who have given the sweat and blood to make this event a successful event. Most importantly, I would like to thank all the participants present here for paying the attention and for the curiosity too. So I would request everyone to please stay tuned for the next talk by Mr. Vidinaran Sai, which will commence tomorrow from 4:45 p.m. to 6:15 p.m. Thank you, sir. Thanks everyone for getting your time out for the event. Thank you, everyone.
All right, folks, thank you for inviting me, and thank you for the audience for attending as well. You have a good day. Bye.
Yes, sir. It was an honor, sir. Thank you.